Hey guys, this is me going over problems 3. This is problem number 3 and problem number 4 on the equilibrium worksheet with the ice tables. A few of you have emailed me and asked me about it, expressing confusion, and I get that. It's a lot more complicated than the other worksheet that I gave you that was just plain writing equilibrium expressions. So this requires a lot of assumptions of you to make about how big or small your x is, what KEQ even means, etc., etc. So ideally, hopefully, you should have already watched the Khan Academy videos for small and large x approximation, because those do go over a couple of practice problems for equilibrium problems that require an ice table. So my hope is that you didn't attempt to do this without watching those, because you would have floundered probably, because I hadn't gone over any examples yet, so hopefully you watched those. Anyway, when you're approaching these problems, you start out much the same as you would start out any problem. You read it, which again, some of you don't like to read problems very thoroughly, and it always confuses me, but this problem wants you to find the equilibrium constant K for the following equilibrium. The initial concentrations of AB and A2D are 0.3 molar before they are mixed, and when equilibrium is reached, the equilibrium concentration of A2D is 0.02 molar. So, looking at this, here's your nice expression. Yes, AB, C2D, blah, 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 that is fake chemicals. Doesn't actually matter what the identity of those chemicals are at all, which is good for you. So, we have our 2AB, which is in a gaseous state. We have C2D. This is supposed to be a subscript, but it didn't copy over easily as a subscript. This is supposed to be a subscript as well, but that's okay. Anyway, this is in a solid state right here. And if you recall from the first set of notes that I gave you, it told you anything that's in a solid state or a liquid state, you ignore that when you're writing the equilibrium expression. So this and this other thing over here that's in a solid state, you are going to straight up ignore when we do our ice table. The only things you're going to address are this one here and that one there, which is good because it simplifies what you need to do. The second thing that you really should do is you should write your equilibrium expression given what you have right now. You don't even need the concentrations or whatever to do that, because again, it's just a template. So over to the right, I'm going to write KEQ equals my products over my reactants. So if I put my product up top, and the only product I have to deal with is this, because if you recall, we crossed out the solid one, my A2D, and yes, I know it's a messy 2, you can figure it out, that is not going to be raised to any power because there is no coefficient before this, and yes, this equation is balanced. You feel free to check if you're not sure. Reactants are going to go on the bottom, so we have our AB over here, so we're going to write that in. And that is actually going to be raised to the second power because of this coefficient of 2 right there. The next thing that you need to do after you have this, because again, this is your roadmap, is you're going to go ahead and you're going to draw an ice table over here. And I like to do that right below my actual expression because that helps me keep track of what is where and what chemical corresponds to which column. So I'm going to go ahead and do that. Boom, here's my ice table. I put you guys on pause while I drew that because you didn't need to painfully watch me draw an ice table for an entire minute. So we have our I row, which is initial. And notice in the problem, it says, hey, initial concentration. So those initial concentrations are going to go here. Our C stands for change, and our E stands for equilibrium. So if you guys recall from our activity the Friday before we left, initially there was a certain condition. Either all the little paper balls were on one side, or half of them were on each side, or whatever it happened to be. Your problem is pretty much always going to tell you what the initial concentration is or what the final concentration is, and you'll have to figure out the other one. So for us right now, our initial concentrations of AB and A2D are 0.3 molar. So we fill that information in. We put in 0.3 here and we put in 0.3 there. And if you recall, these don't get counted. So I'm just going to go ahead and I'm going to draw lines saying, hey, nope, we don't even need to worry about those in the problem. Then it also gives us one other piece of information. It says the equilibrium concentration of A2D is 0.02, which is going to go right there, 0.02, which is fine. Now, that tells us something here, because obviously this has to be what changed between here and here, because if initially you started here and you end up here, something has to change in the middle. So clearly we subtracted something to get from 3 to 0.02. So our change concentration is going to be 0.3 minus 0.02, which is awesome for us, because it allows us to know what our change in concentration is. We don't even have to fill in an X or make any assumptions whatsoever. We know that our change concentration is 0.28, which is great. Now, for this here, these two columns that we have to fill in, these two boxes, your change concentration has to be much the same for both of these. And it depends on how much one of them changed. So if we have subtracted effectively, because this is subtraction here, and you know that because it went from 0.3 to 0.02. We've subtracted 0.28 moles per liter to get from here to here. So it makes sense that if we're subtracting a concentration here, we should probably be adding a concentration over here, which means that this change in concentration is going to be a positive number. Now, how much do we add over here? Because it's not as simple as just adding 0.28 over here. In this column, you have to factor in your coefficients. So you theoretically would be adding up top, and I'm going to write it kind of small up here, you would be adding 2x. And the reason that you know that if you watch those con videos is because you have a 2 here, and your concentration is unknown at this point for this particular chemical. So you have X concentration, but you know that you're adding 2 molar amounts of whatever that concentration is, because you have that 2 coefficient. So how X was 0.28 over here, and you know that it's 0.28 equals X because there's not a 2 up here or any other number, so it's 1x. So if this is x, you're 0.28, and you're adding 2 of x, you're adding 2 times 0.28 over here. And that's super messy, but that's okay. So if you're adding 2 times 0.28, altogether you are adding 0.56 over there. Now, this final box down here is the total of everything here. So if you have over here, this is filled in, you have 0.3 minus 0.02, giving you 0.28, minus 0.28 is a change. If you total 0.3 and negative 0.28, you end up with 0.2. So if we total 0.3 plus 0.56 over here, we end up with 0.86. So we put that answer here. So this is a 0.86, which is good for us because now we know what our equilibrium concentrations are. So now we can go and we can do and fill in this equilibrium expression. So over here, we're going to rewrite K eq equals our products over our reactants, just like we did before. So our products over here, that is going to be our 0.02. Once again, not at all raised to an exponent. And then on the bottom, we have our AB concentration, which we just figured out was 0.86. So we have our 0.86. That was raised to the power of 2. And then we can go ahead and do that math. And once we figure that out, the answer turns out to be 0.027. 0.027 is our KEQ. And so you know that because you've done this, you've done the equilibrium expression, you've done the ICE table, you've done all of that. So this guy turns out to be your answer, and that is all you had to do for that problem. And I'm running short on time on how much I can say in this video because Screencast only lets you do 15-minute videos. So I'm actually, for number 4, going to split that into a part 2 video, which I will post separately, but you'll have access to both of those. So hold on and click on the next video for part 2.